P versus NP problem is a major unsolved problem in computer science. Informally, it asks whether every problem whose solution can be quickly verified by a computer can also be quickly solved by a computer. It was introduced in 1971 by Stephen Cook in his seminal paper The Complexity of Theorem Proving Procedures, and is considered by many to be the most important open problem in the field. It is one of the 7 Millennium Prize Problems selected by the Clay Mathematics Institute to carry a $1 million prize for the first correct solution. The informal term quickly used above means the existence of an algorithm for the task that runs in polynomial time. The general class of questions for which some algorithm can provide an answer in polynomial time is called class P, or just P. For some questions, there is no known way to find an answer quickly, but if one is provided with information showing what the answer is, it may be possible to verify the answer quickly. The class of questions for which an answer can be verified in polynomial time is called NP. Consider the subset sum problem, an example of a problem that is easy to verify, but whose answer may be difficult to compute. Given a set of integers, does some non-empty subset of them sum to 0? For instance, does a subset of the set a 2, a 3, 15, 14, 7, a 10 add up to 0? The answer yes, because the subset a 2, a 3, a 10, 15 adds up to 0 can be quickly verified with 3 additions. However, there is no known algorithm to find such a subset in polynomial time, but such an algorithm exists if P equals NP. Hence this problem is in NP but not necessarily in P. An answer to the PAR equals NP question would determine whether problems that can be verified in polynomial time, like the subset sum problem, can also be solved in polynomial time. If it turned out that PA permel NP, it would mean that there are problems in NP that are harder to compute than to verify. They could not be solved in polynomial time, but the answer could be verified in polynomial time. Aside from being an important problem in computational theory, a proof either way would have profound implications for mathematics, cryptography, algorithm research, artificial intelligence, game theory, multimedia processing, philosophy, economics and many other fields. Context: the relation between the complexity classes P and NP is studied in computational complexity theory, the part of the theory of computation dealing with the resources required during computation to solve a given problem. The most common resources are time and space. In such analysis, a model of the computer for which time must be analyzed is required. Typically such models assume that the computer is deterministic and sequential. In this theory, the class P consists of all those decision problems that can be solved on a deterministic sequential machine in an amount of time that is polynomial in the size of the input. The class NP consists of all those decision problems whose positive solutions can be verified in polynomial time given the right information, or equivalently, whose solution can be found in polynomial time on a non-deterministic machine. Clearly, P-NP. Arguably the biggest open question in theoretical computer science concerns the relationship between those two classes. Is P equal to NP? In a 2002 poll of 100 researchers, 61 believed the answer to be no, 9 believed the answer is yes, and 22 were unsure. 8 believed the question may be independent of the currently accepted axioms and therefore is impossible to prove or disprove. In 2012, 10 years later, the same poll was repeated. The number of researchers who answered was 151, 126 believed the answer to be no, 12 believed the answer is yes, 5 believed the question may be independent of the currently accepted axioms and therefore is impossible to prove or disprove, 8 said either don't know or don't care or don't want the answer to be yes nor the problem to be resolved. NP complete. To attack the P equals NP question, the concept of NP completeness is very useful. NP complete problems are a set of problems to each of which any other NP problem can be reduced in polynomial time, and whose solution may still be verified in polynomial time. That is, any NP problem can be transformed into any of the NP complete problems. Informally, an NP complete problem is an NP problem that is at least as tough as any other problem in NP, NP-hard problems are those at least as hard as NP problems, that is, all NP problems can be reduced to them. NP-hard problems need not be in NP, that is, they need not have solutions verifiable in polynomial time. For instance, the Boolean satisfiability problem is NP-complete by the Cooke-Levin theorem, so any instance of any problem in NP can be transformed mechanically into an instance of the Boolean satisfiability problem in polynomial time. The Boolean satisfiability problem is one of many such NP-complete problems. If any NP-complete problem is in P, then it would follow that P equals NP. Unfortunately, many important problems have been shown to be NP-complete, and not a single fast algorithm for any of them is known. Based on the definition alone, it is not obvious that NP-complete problems exist. A trivial and contrived NP-complete problem can be formulated as, given a description of a Turing machine M guaranteed to halt in polynomial time, does there exist a polynomial size input that M will accept? It is in NP because it is simple to check whether M accepts the input by simulating M. It is NP-complete because the verifier for any particular instance of a problem in NP can be encoded as a polynomial time machine M that takes the solution to be verified as input. Then the question of whether the instance is a yes or no instance is determined by whether a valid input exists. The first natural problem proven to be NP-complete was the Boolean satisfiability problem. As noted above, this is the Cooke-Levin theorem. Its proof that satisfiability is NP-complete contains technical details about Turing machines as they relate to the definition of NP. However, after this problem was proved to be NP-complete, proof by reduction provided a simpler way to show that many other problems are also NP-complete, including the subset sum problem discussed earlier. Thus, a vast class of seemingly unrelated problems are all reducible to one another, and are in a sense the same problem. Harder problems. Although it is unknown whether P equals NP, problems outside of P are known. A number of succinct problems are known to be exp-time complete. Because it can be shown that PASHSH exp-time, these problems are outside P, and so require more than polynomial time. In fact, by the time hierarchy theorem, they cannot be solved in significantly less than exponential time. Examples include finding a perfect strategy for chess and some other board games. The problem of deciding the truth of a statement in Presburger arithmetic requires even more time. Fisher and Rubin proved in 1974 that every algorithm that decides the truth of Presburger statements has a runtime of at least for some constant c. Here, n is the length of the Presburger statement. Hence, the problem is known to need more than exponential runtime. Even more difficult are the undecidable problems, such as the halting problem. They cannot be completely solved by any algorithm, in the sense that for any particular algorithm there is at least one input for which that algorithm will not produce the right answer. It will either produce the wrong answer, finish without giving a conclusive answer, or otherwise run forever without producing any answer at all. Problems in NP not known to be NP or NP-complete. It was shown by Ladner that if PA permil NP, then there exist problems in NP that are neither NP nor NP-complete. Such problems are called NP-intermediate problems. The graph isomorphism problem, the discrete logarithm problem and the integer factorization problem are examples of problems believed to be NP-intermediate. They are some of the very few NP problems not known to be NP or to be NP-complete. The graph isomorphism problem is the computational problem of determining whether two finite graphs are isomorphic. An important unsolved problem in complexity theory is whether the graph isomorphism problem is in P, NP-complete, or NP-intermediate. The answer is not known, but it is believed that the problem is at least not NP-complete. If graph isomorphism is NP-complete, the polynomial time hierarchy collapses to its second level. Since it is widely believed that the polynomial hierarchy does not collapse to any finite level, it is believed that graph isomorphism is not NP-complete. The best algorithm for this problem, due to Laszlo Babay and Eugene Lux, has runtime 20, ASHNLOG, n for graphs with n vertices. The integer factorization problem is the computational problem of determining the prime factorization of a given integer. Phrased as a decision problem, it is the problem of deciding whether the input has a factor less than k. No efficient integer factorization algorithm is known, and this fact forms the basis of several modern cryptographic systems, such as the RSA algorithm. The integer factorization problem is in NP and in co-NP. If the problem is NP-complete, the polynomial time hierarchy will collapse to its first level. The best-known algorithm for integer factorization is the general number field sieve, which takes expected time to factor an n-bit integer. However, the best-known quantum algorithm for this problem, Shor's algorithm, does run in polynomial time. Unfortunately, this fact doesn't say much about where the problem lies with respect to non-quantum complexity classes. Does P mean easy? All of the above discussion has assumed that P means easy, and not in P means hard, an assumption known as Cobham's thesis. It is a common and reasonably accurate assumption in complexity theory. However, it has some caveats. First, it is not always true in practice. A theoretical polynomial algorithm may have extremely large constant factors or exponents, thus rendering it impractical. On the other hand, even if a problem is shown to be NP-complete, and even if PA permel NP, there may still be effective approaches to tackling the problem in practice. There are algorithms for many NP-complete problems, such as the knapsack problem, the traveling salesman problem and the Boolean satisfiability problem, that can solve to optimality many real-world instances in reasonable time. The empirical average case complexity of such algorithms can be surprisingly low. A famous example is the simplex algorithm in linear programming, which works surprisingly well in practice. Despite having exponential worst-case time complexity, it runs on par with the best-known polynomial time algorithms. Second, there are types of computations which do not conform to the Turing machine model on which P and NP are defined, such as quantum computation and randomized algorithms. Reasons to believe PA permel NP. According to polls, many computer scientists believe that PA permel NP. A key reason for this belief is that after decades of studying these problems, no one has been able to find a polynomial time algorithm for any of more than 3,000 important known NP-complete problems. These algorithms were sought long before the concept of NP-completeness was even defined. Furthermore, the result P equals NP would imply many other startling results that are currently believed to be false, such as NP equals co-NP and P equals PH. It is also intuitively argued that the existence of problems that are hard to solve but for which the solutions are easy to verify matches real-world experience. If P equals NP, then the world would be a profoundly different place than we usually assume it to be. There would be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it's found. On the other hand, some researchers believe that there is overconfidence in believing PA permel NP and that researchers should explore proofs of P equals NP as well. For example, in 2002 these statements were made. The main argument in favor of PA permel NP is the total lack of fundamental progress in the area of exhaustive search. This is, in my opinion, a very weak argument. The space of algorithms is very large and we are only at the beginning of its exploration. The resolution of Fermat's last theorem also shows that very simple questions may be settled only by very deep theories. Being attached to a speculation is not a good guide to research planning. One should always try both directions of every problem. Prejudice has caused famous mathematicians to fail to solve famous problems whose solution was opposite to their expectations, even though they had developed all the methods required. Consequences of the resolution of the problem. One of the reasons the problem attracts so much attention is the consequences of the answer. Either direction of resolution would advance theory enormously, and perhaps have huge practical consequences as well. P equals NP, a proof that P equals NP could have stunning practical consequences, if the proof leads to efficient methods for solving some of the important problems in NP. It is also possible that a proof would not lead directly to efficient methods, perhaps if the proof is non-constructive, or the size of the bounding polynomial is too big to be efficient in practice. The consequences, both positive and negative, arise since various NP-complete problems are fundamental in many fields. Cryptography, for example, relies on certain problems being difficult. A constructive and efficient solution to an NP-complete problem such as 3SAT would break most existing crypto systems, including public key cryptography, a foundation for many modern security applications such as secure economic transactions over the Internet, and symmetric ciphers such as AES or 3DES, used for the encryption of communications data. One-way functions used in cryptographic hashing. The problem of finding a preimage that hashes to a given value must be difficult to be useful, and ideally should require exponential time. However, if p equals np, then finding a preimage m can be done in polynomial time, through reduction to SAT. These would need to be modified or replaced by information theoretically secure solutions not inherently based on PNP equivalence. On the other hand, there are enormous positive consequences that would follow from rendering tractable many currently mathematically intractable problems. For instance, many problems in operations research are NP-complete, such as some types of integer programming, and the traveling salesman problem, to name two of the most famous examples. Efficient solutions to these problems would have enormous implications for logistics. Many other important problems, such as some problems in protein structure prediction, are also NP-complete. If these problems were efficiently solvable, it could spur considerable advances in biology. But such changes may pale in significance compared to the revolution an efficient method for solving NP-complete problems would cause in mathematics itself. Gar paragraph Dell, in his early thoughts on computational complexity, noted that a mechanical method that could solve any problem would revolutionize mathematics. If there really were a machine with I.N., a 1/4 KAN, this would have consequences of the greatest importance. Namely, it would obviously mean that in spite of the undecidability of the Insky-Dunks problem, the mental work of a mathematician concerning yes or no questions could be completely replaced by a machine. After all, one would simply have to choose the natural number n so large that when the machine does not deliver a result, it makes no sense to think more about the problem. Similarly, Stephen Cook says, it would transform mathematics by allowing a computer to find a formal proof of any theorem which is a proof of a reasonable length, since formal proofs can easily be recognized in polynomial time. Example problems may well include all of the CMI prize problems. Research mathematicians spend their careers trying to prove theorems, and some proofs have taken decades or even centuries to find after problems have been stated. For instance, Fermat's last theorem took over 3 centuries to prove. A method that is guaranteed to find proofs to theorems, should one exist of a reasonable size, would essentially end this struggle. Donald Knuth has stated that he has come to believe that P equals NP, but is reserved about the impact of a possible proof. I don't believe that the equality P equals NP will turn out to be helpful even if it is proved, because such a proof will almost surely be non-constructive. PA permil NP, a proof that showed that PA permil NP would lack the practical computational benefits of a proof that P equals NP, but would nevertheless represent a very significant advance in computational complexity theory and provide guidance for future research. It would allow one to show in a formal way that many common problems cannot be solved efficiently, so that the attention of researchers can be focused on partial solutions or solutions to other problems. Due to widespread belief in PA permil NP, much of this focusing of research has already taken place. Also, PA permil NP still leaves open the average case complexity of hard problems in NP. For example, it is possible that SAT requires exponential time in the worst case, but that almost all randomly selected instances of it are efficiently solvable. Russell Impagliazzo has described 5 hypothetical worlds that could result from different possible resolutions to the average case complexity question. These range from algorithmica, where P equals NP and problems like SAT can be solved efficiently in all instances, to cryptomania, where PA permel NP in generating hard instances of problems outside P is easy, with three intermediate possibilities reflecting different possible distributions of difficulty over instances of NP hard problems. The world, where PA permel NP but all problems in NP are tractable in the average case is called heuristica in the paper. A Princeton University workshop in 2009 studied the status of the five worlds. Results about difficulty of proof, although the P equals NP problem itself remains open despite a $1 million prize and a huge amount of dedicated research, efforts to solve the problem have led to several new techniques. In particular, some of the most fruitful research related to the P equals NP problem has been in showing that existing proof techniques are not powerful enough to answer the question, thus suggesting that novel technical approaches are required. As additional evidence for the difficulty of the problem, essentially all known proof techniques in computational complexity theory fall into one of the following classifications, each of which is known to be insufficient to prove that PA permel NP. These barriers are another reason why NP-complete problems are useful. If a polynomial time algorithm can be demonstrated for an NP-complete problem, this would solve the P equals NP problem in a way not excluded by the above results. These barriers have also led some computer scientists to suggest that the P versus NP problem may be independent of standard axioms systems like ZFC. The interpretation of an independence result could be that either no polynomial time algorithm exists for any NP-complete problem, and such a proof cannot be constructed in ZFC, or that polynomial time algorithms for NP-complete problems may exist, but it's impossible to prove in ZFC that such algorithms are correct. However, if it can be shown, using techniques of the sort that are currently known to be applicable, that the problem cannot be decided even with much weaker assumptions extending the P-no axioms for integer arithmetic, then there would necessarily exist nearly polynomial time algorithms for every problem in NP. Therefore, if one believes that not all problems in NP have efficient algorithms, it would follow that proofs of independence using those techniques cannot be possible. Additionally, this result implies that proving independence from PA or ZFC using currently known techniques is no easier than proving the existence of efficient algorithms for all problems in NP. It should also be noted that there are statements which are independent in ZFC and cannot be verified as such by any Turing machine, and so in this sense it is possible for a problem to never possibly be proven true, false, or even independent of ZFC. It is not currently known whether or not P equals NP is such a problem. Claimed solutions. While the P versus NP problem is generally considered unsolved, many amateur and some professional researchers have claimed solutions. Ueginger has a comprehensive list. An August 2010 claim of proof that PA permel NP, by Vinay Dialalekar, researcher at HP Labs, Palo Alto, received heavy internet and press attention after being initially described as seeming to be a relatively serious attempt by two leading specialists. The proof has been reviewed publicly by academics, and Neil Immerman, an expert in the field, had pointed out two possibly fatal errors in the proof. In September 2010, Dialalekar was reported to be working on a detailed expansion of his attempted proof. However, opinions expressed by several notable theoretical computer scientists indicate that the attempted proof is neither correct nor a significant advancement in the understanding of the problem. This assessment prompted a May 2013 The New Yorker article to call the proof attempt thoroughly discredited. Logical characterizations. The P equals NP problem can be restated in terms of expressible certain classes of logical statements, as a result of work in descriptive complexity. Consider all language of finite structures with a fixed signature including a linear order relation. Then, all such languages in P can be expressed in first-order logic with the addition of a suitable least fixed point combinator. Effectively, this, in combination with the order, allows the definition of recursive functions. As long as the signature contains at least one predicate or function in addition to the distinguished order relation, so that the amount of space taken to store such finite structures is actually polynomial in the number of elements in the structure, this precisely characterizes P. Similarly, NP is the set of languages expressible in existential second-order logic that is, Second-order logic restricted to exclude universal quantification over relations, functions, and subsets. The languages in the polynomial hierarchy, pH, correspond to all of second-order logic. Thus, the question is a proper subset of NP can be reformulated as is existential second-order logic able to describe languages that first-order logic with least fixed point cannot? The word existential can even be dropped from the previous characterization, since P equals NP if and only if P equals pH. Polynomial time algorithms. No algorithm for any NP complete problem is known to run in polynomial time. However, there are algorithms for NP complete problems with the property that if P equals NP, then the algorithm runs in polynomial time. The following algorithm, due to Levin, is such an example below. It correctly accepts the NP complete language subset sum. It runs in polynomial time if and only if P equals NP. Algorithm that accepts the NP complete language subset sum. This is a polynomial time algorithm if and only if P equals NP. Polynomial time means it returns yes in polynomial time when the answer should be yes, and runs forever when it is no. Input, S equals a finite set of integers, output, yes if any subset of S adds up to 0. Runs forever with no output otherwise. Note, program number P is the program obtained by writing the integer P in binary, then, considering that string of bits to be a program. Every possible program can be generated this way, though most do nothing, because of syntax errors. For n equals 1. For P equals 1. N, run program number P for n steps with input S, if the program outputs a list of distinct integers, and the integers are all in S, and the integers sum to 0 then, output yes, and halt. If, and only if, P equals NP, then this is a polynomial time algorithm accepting an NP complete language. Accepting means it gives yes answers in polynomial time, but is allowed to run forever when the answer is no. This algorithm is enormously impractical, even if P equals NP. If the shortest program that can solve subset SUM in polynomial time is b bits long, the above algorithm will try at least 2-1 other programs first. Formal definitions for P and NP. Conceptually, a decision problem is a problem that takes as input some string W over an alphabet I pound, and outputs yes, or no. If there is an algorithm that can produce the correct answer for any input string of length n and at most cnk steps, where k and c are constants independent of the input string, then we say that the problem can be solved in polynomial time and we place it in the class P formally. P is defined as the set of all languages that can be decided by a deterministic polynomial time Turing machine. That is, where and a deterministic polynomial time Turing machine is a deterministic Turing machine M that satisfies the following two conditions: M halts on all input W and there exists such that, where O refers to the big O notation and NP can be defined similarly using non-deterministic Turing machines. However, a modern approach to define NP is to use the concept of certificate and verifier. Formally, NP is defined as the set of languages over a finite alphabet that have a verifier that runs in polynomial time, where the notion of verifier is defined as follows. Let L be a language over a finite alphabet, I pound. LLNP if, and only if, there exists a binary relation and a positive integer k such that the following two conditions are satisfied, for all, such that R and the language over is decidable by a Turing machine in polynomial time. A Turing machine that decides LR is called a verifier for L and AY such that R is called a certificate of membership of X in L. In general, a verifier does not have to be polynomial time. However, for L to be an NP, there must be a verifier that runs in polynomial time. Example, let. Clearly, the question of whether a given X is a composite is equivalent to the question of whether X is a member of composite. It can be shown that composite NP by verifying that it satisfies the above definition. Composite also happens to be in P. Formal definition for NP completeness. there are many equivalent ways of describing NP completeness. Let L be a language over a finite alphabet I pound. L is NP complete if, and only if, the following two conditions are satisfied, L in P. And, any la euro squared in NP is polynomial time reducible to L, where if, and only if, the following two conditions are satisfied, there exists phi I pound a I pound such that for all W in I pound we have. And, there exists a polynomial time Turing machine that halts with f, W, on its tape on any input W. Popular culture, the film Traveling Salesman, by director Timothy Lanswan, is the story of four mathematicians hired by the U.S. government to solve the P versus NP problem. See also, Game complexity, unique games conjecture, unsolved problems in computer science, unsolved problems in mathematics, references. Notes. Further reading, Frankel, A.S. Lichtenstein, Decomputing a perfect strategy for NN chess requires time exponential in N doi, 10.1007 over 3-540-10843-2 plus 23 Gary, Michael. Johnson, David. Computers and Intractability, A Guide to the Theory of NP Completeness. San Francisco, W. H. Freeman and Company. ISBN A0-7167-1045-5 Goldreich, Oded. P, NP, and NP Completeness. Cambridge, Cambridge University Press. ISBN A978-0-521-12254-2 Online drafts, Immermann, and Languages which Capture Complexity Classes. Siam Journal of Computing 16, 760 €778 doi, 10.1137/02160510 Corman, Thomas. Introduction to Algorithms. Cambridge, MIT Press. ISBN A0-262-03293-7 Papadimitriou, Christos. Computational Complexity. Boston, Addison Wesley. ISBN A0-201-53082-1 Fortnow, L. The Status of the P versus NP Problem. Communications of the ACM 52, 78 doi, 10.1145/1562164.1562186 Fortnow, L. Garsarch, W. Computational Complexity Fortnow, Lance. The Golden Ticket, P, NP, and the Search for the Impossible ISBN 9780691156491. Princeton University Press. Princeton, N.J., External links. The Clay Mathematics Institute Millennium Prize Problems, the Clay Math Institute Official Problem Description PDF 118 KB, Gerard J. Wedinger. The P versus NP page. A list of links to a number of purported solutions to the problem. Some of these links state that P equals NP, some of them state the opposite. It is probable that all these alleged solutions are incorrect. Complexity Zoo, Class P, Complexity Zoo, Class NP, Scott Aronson Eshdale Optimized blog, Reasons to Believe, a list of justifications for the belief that PA permil NP.